Hi everyone. In this video we're going to start talking about section 6.2 which is on one-to-one and inverse functions. Okay, and so we're going to use the ideas from our composite function section 6.1 here when we talk about inverse functions. But first we're going to talk about one-to-one functions because they in fact also have a direct impact on inverse functions. Okay, so first we want to talk about a one-to-one function, and the formal definition of a one-to-one function is a function is one-to-one if any two different inputs in the domain correspond to two different outputs in the range. That is, that for 2 points x1 and x2, okay, if there are two different inputs of the function f, okay, then and you get different points back, then f is one-to-one. If x1 and x2 are two different inputs to the function, then f is one-to-one if the function values are not the same, and that has to stand for any two inputs. Now, that definition is really confusing, probably, okay, or probably doesn't help you understand what a one-to-one function is, but a one-to-one function is actually pretty simple, okay? And so you have to remember back to our definition of a function, just any old function, said that 1x goes to 1y. Okay, and so we have two examples down here. I'll call them 1 and 2. And we'll look at number 2 first. Number 2 here is an example of a regular function. Right? So for a regular function, say regular function here, 1x has to go to 1y, okay? And it's also true that different x's can, I'm going to run out of space here, different x's can go to the same y. Okay, and so that's an example here in number 2. I can't have multiple x's go, I can't have the same x go to multiple y's. That's a problem. That means it's not a function. And so, for example, if cat went to 11 and to 10 for some reason, okay, then it would not be a function. But all we need is that 1x goes to 1y. And the reason why we look at this example, or this example is important, number 2, is that we have different x's going to the same y. So both dogs and cats have probably an average life expectancy, if you don't think about different breeds, of 11 years. Something like a duck, a lion, and a pig have 10, okay, and a rabbit has 7. This is an important example because this is a function, okay, but it is not a one-to-one function, okay? Not a one-to-one function. That's what we see, or that's of course what we're interested in. And the definition, or the part of the definition that's important, it says that if I have different inputs, okay, so actually to back up, before you have to be a one-to-one function, you have to be a function in general. So it's always true for any type of function that this 1x goes to 1y rule is adhered to. And this is adding something more onto it. This is saying that if I have two different inputs, say x1 and x2, that leads to two different outputs. And so what a one-to-one function adds is that 1y has to go to 1x as well. Okay? So it means that 1x has to go to 1y, just like in a regular function, but also that that same y can only be related to x, the 1x. Okay? And so number 2 is a problem because both dog and cat go to 11. So that's not a one-to-one function. But you see over on the left side, we have example with a state and then population in millions. And you'll see that 1x goes to 1y, but that relationship also holds if you go backwards. There's only one y for each. Y only goes to 1x as well. Okay, so there's this relationship that they're in pairs. Okay, and no state can share the same population. If we're looking at that example. Okay, so hopefully that made a little bit of sense. Okay, so one-to-one function. Each x in the domain has one and only one image in the range, and an image is what it's connected to. So this is just an example that the book gives. Okay. Example 2 here, or part B, it's not one-to-one because both x1 and x2 go to y1. Okay, but it is a function because only one x goes to one y. And example part C, okay, part A is a one-to-one function, but part C here is not a function at all because x, we have one x going to multiple y's. So those are the 3 different examples graphically of types of functions that we know. Now, it's often helpful to view these, if a function is one-to-one, graphically. Okay, so it's easiest to tell if a function is one-to-one by graphing the function and looking at it. And so if you'll remember, way back to regular functions, we had a vertical line test, and if the function or the relation passed the vertical line test, then it was a function. Well, now we have a horizontal line test, okay? And the horizontal line test is for one-to-one functions. It works the same as the vertical line test, okay? If the horizontal line, if I pass it through the entire function and it only hits at most once, then the function is one-to-one. But if the horizontal line hits the function more than once at any point along the function, then it is not a one-to-one function, okay? So it says it more elegantly here. If every horizontal line intersects the graph of a function f at most 1 point, then f is one-to-one. Okay, so basically, if you draw a horizontal line at any point on the function, okay, and it hits 2 or more times, then it's not one-to-one. If it only hits 1 or 0 times, then it is one-to-one. So here's 2 examples. So just 2 more quick examples of x squared and then x cubed, 2 common types of functions that we see. And so you'll look and see in the x squared case clearly, if you draw a horizontal line at any point except for 0, you're going to hit the function 2 times. Okay, and so x squared is not a one-to-one function. In contrast, if you look at x cubed, you'll see that it is a one-to-one function because any time you draw a horizontal line for x cubed, you're going to get only one intersection. So x cubed is a one-to-one function. And so this leads us to our first your turn. Okay, our first your turn. I want you to state whether or not the following functions are one-to-one. Okay? And so you'll want to graph them, but for both of them, you only have to give me a really rough sketch of what they're going to look like. Okay, so this leading term, so if we look at example number 1, if I label this number 1 and number 2, if you look at number 1, it might take a little bit to graph it, but you can use our topic that we talked about a little while ago, the end behavior of a function, to look and say that the leading term is x squared, and so it's going to look kind of like an x squared function. Okay, and then 4x shouldn't be too hard. That's a line. Okay, and so give very rough sketches, but enough to tell if a horizontal line test will pass or not, and that way you'll be able to tell me if the function is 1-to-1 or not. Okay, so that's the your turn, and I have one more slide to go through until we end this first video. And so 1-to-1 functions have a relationship between increasing and decreasing. So I know we talked about how to tell if a function is increasing or decreasing a long while ago, but 1-to-1 functions have a direct relationship with this. And so that relationship is, if a function is increasing on some interval I, then that function is a 1-to-1 function on I. And so what does that mean? So if I draw just a simple xy plane, and I add a line here from 0 to, we'll say this is 10, okay? Then on the interval 0 to 10, if it's increasing the entire time, which in my example it is, then that function is 1-to-1, because if you draw any horizontal line during that time, then it only hits 1. In contrast, if I'd have a function that looks like this from 0 to, say, 5, and I look on the interval 0 to 5, you'll see that it starts out decreasing and then hits some number here and then starts to increase. So since it's not either increasing or decreasing the entire time, it doesn't pass the horizontal line test and hence isn't 1-to-1. Okay, so if a function is increasing or decreasing the entire time on some interval, then it's 1-to-1 on the interval. Okay, and so that's a point that we won't dwell on for long, but it is important. Okay, and that's the end of this video. I'll see you for the second half in just a little bit, probably.